All right. I've received a lot of requests recently from people who saw these models that I've been sharing on Facebook, uh, but didn't really necessarily understand what they meant. So I wanted to take a couple of minutes to just explain those in case anyone is interested to get a better understanding of how fast this epidemic is spreading and also what it is that social distancing does to slow the spread of the epidemic. So let me show these one by one. The first link is just to look at the data itself with a very simple model that's fit to it. So if you open up that link, it takes you to a website called Desmos. We've got a nice table here on the left which shows the day of March and the number of cases. So it looks like on March 5th there were 227 cases of coronavirus, and by March 15th that had risen to 3,774. And the graph here on the right with the green dots actually shows the raw data. And then the black represents our best fit model to describe the trend that we're seeing. And if you're interested in the equation, that's actually stored over here on the left down below. And you see that is an exponential function. So it's some constant times the e, the number 2.71 roughly, times some constant times x. And that's a function that grows very, very quickly. Now, the specifics of that may not be of all that much interest to you, but a couple of things I want to point out are, first of all, this value of r squared, which measures how good of a model do we have? How well does it fit the trend in the data? A value of 1 would be perfection, and we have a value of 0.9997, which means an exponential is an excellent fit to the data. In fact, you will not rarely ever in practice see a value of r squared that's better than that. So what that also means is that this epidemic is growing very rapidly because exponential functions grow faster than most of the typical functions that you're used to hearing about. The second thing to notice here is that there's a nice little slider to let you play around with forecasting. So right now the value is set to 50. Let me scroll back to 16 since today is March 16, and it says that based on the model thus far, we should have around 4,920 cases by the end of today. Now I haven't checked the numbers, but that seems very plausible based on where we've been. But let's turn the clock forward 7 days. So we'll look at March 23rd and see what's happened to the number of cases. And here it's predicting that we will have gone from between 4,000 and 5,000 to all the way up to 33,000. So growing very, very quickly. And if this pattern continues, you look at mid-March, you'll see that the number of cases will reach 13 million. And that would obviously be very bad news. And once you factor in that 2% mortality rate that they've been reporting, the number of deaths is going to be extremely high and very, very troubling, I think, for all of us. So the hope is that this model does not hold indefinitely. And some of the measures that have been taken recently in terms of encouraging people to avoid large gatherings, closing restaurants, I think have a potential to definitely slow this down quite a bit. So the hope is this pattern does not continue and that 13 million number is not something that we actually reach. But if we were to do nothing, I think there's a decent chance that that would be pretty close to where we'd be sometime in April. All right, so that's the first model. Relatively straightforward. We're just plugging in numbers to an exponential function, which seems to fit the trend thus far to create some sort of forecast for where things are headed. All right, the second type of model is a little bit more complicated, and it's actually a simulation of what an epidemic looks like. Now, this may take a minute to load on your computer, so while it's getting set up, let me just give you some basic understanding of what the model does. It basically simulates 3 different events that cause the number of people of each category in the model to change. So we've got 4 categories. We have people who are susceptible to the disease. We have people who are infected with the coronavirus. We've got people who have recovered and are therefore immune, or at least that's what we hope. And lastly, we have people who have died. So 4 categories. Everyone in the population has got to fall in one of those 4 categories. And here I'm using an initial population size of 300 million, which is in the ballpark of the size of the US population. All right. Now, there's a whole bunch of other parameters, and we don't want to focus on those right now. But I want to point out that if you actually want to run the model and see how it works, you need to follow the instructions here at the top. It says to run the notebook, click Restart and Run All from the kernel menu above. So I found kernel. Scroll down. It says Restart and Run All. And that's actually going to run the simulation so that we can see the results and then play around with some of the parameters to see how it affects the answers. All right, so when you do that, if you scroll down, you'll see a nice little plot here. It has, well, 4 different colors. The blue represents the number of people who are susceptible over time. The green represents the number of people who have recovered. Now, if we've done our job well, we will have a lot of people who are susceptible at the end of the epidemic because that means that they never actually got sick. On the other hand, if we have a lot of people who recovered, that means a ton of people got sick, and well, that's also going to lead to a lot of deaths. And so the black curve down at the bottom, it's a relatively small fraction of the population because remember the mortality rate for this is somewhere between 2 and 3% thus far. So we're not going to have, a huge fraction of the population who dies, but we really don't want to have a large number of people getting sick at all because that will inevitably lead to far too many deaths. All right, the other curve to pay attention to is the red one. The red represents the number of infected, and if you see a very high peak value here, like right now, the solid red curve has a peak around 20% of the population. That means that, well, a lot of people were sick all at one time. And that would be problematic because the hospital systems in our country are not capable of handling that kind of load. The hospitals would be overrun if that were to happen. And so the hope is that what we can do is change our behavior so that we don't have something that looks like these solid curves, but rather we have something less severe like the dashed curves here. So what the model is doing is it's assuming that up to time t, which right now I've got a slider that says t is equal to 100, people behave in a consistent way. They're acting as if there is no epidemic. And then at time t equals 100, we're going to change their behavior and see what the effect is on the spread throughout the country. In this case, the change in behavior is going to be a reduction of 40%. So this last slider here represents how much we reduce our contact with other people. And so initially, the contact rate is set to be 20, which means people interact with about 20 people a day. Excuse me. But then after this time 100, we're going to reduce that by 40%, so from 20 down to 12, and see what that does to the spread of the epidemic. All right, so you notice the red curve goes up, up, up when in the original case where we have no social distancing, but after social distancing, the peak is actually much, much lower, which is good news, as I mentioned, because that means that we're actually placing less of a burden on our hospitals, and so they're going to be able to care for people much more effectively. The other thing to notice is that the blue solid curve reaches a minimum value of around 20% at the very end. That means at the end of the day, 20% of people are susceptible to disease, and the other 80% are therefore people who got the disease at some point. Most of those recovered, that's the green, but some small fraction also died, and that's the black. Now, if we introduce social distancing, meaning we reduce our contact rate with other people, you see that the peak, the final value of the number of susceptible people is much higher. So here it's looking like somewhere around 70% of people are susceptible at the end, which means only 30-some% of people actually got the disease at some point. So this is very effective at reducing the total number of cases. And time 100 is actually pretty close to where we are right now. It's been about 100 days since the first cases were introduced to our country. And so this is a plausible type of scenario for what the effects of social distancing could be on the coronavirus spread in the US. All right, so let's see what happens if instead of responding immediately, we delay. So we're going to change the value of t here to push back this intervention time where people change their behavior to a later date. So let's say we push it back around 20 days or so. All right, well, it's around 20. Notice what happened. First of all, the peak of the red curve, the red dash curve that is, got much higher. So at the worst point, a lot more people were actually sick. So that's, again, putting more strain on our doctors and nurses and the hospitals. The second thing to notice is that the final value of the blue curve, the number of people who are susceptible, has dropped. It was around 70%. Now it's more around 60%, which means an extra 10% of the people got coronavirus in this particular case. And as we increase t, as we delay our interactions, we'll see that eventually it has very little effect. So once the epidemic has peaked, really we don't reduce the number of infections all that much by trying to reduce our contact rate by social distancing. All right, and at the bottom you can actually see raw numbers in terms of the number of infections and deaths according to the two models. In the very extreme case where no one changes their behavior, we've got around 80% of the population ultimately gets infected, which means between 2 and 3% are dying here, because I've got the death rate set to, the mortality rate rather, set to 3%. But on the other hand, when we intervene early on, we can reduce that down from 80% to 33%. So that means 50% of the country does not get sick in that scenario, whereas they would have in the original. Now, I don't think you should put too much stock in these numbers. Again, this is not meant to be a hyper-realistic simulation. We're not taking into account geography here. It's meant to be more qualitative, just to see that intervening early on can have a big effect on the number of people that are ultimately going to get sick. And so even if you do create a more complicated simulation where you're actually modeling mobility on the transportation network and you're taking into account population density and all these factors, you would expect to see a similar qualitative behavior, even if the exact numbers aren't exactly the same. All right, so I hope that watching this video helps you understand the model just a little bit more. Let me quickly mention the last couple of parameters in case anyone is curious. So here we've got C, which represents the contact rate. Right now, people are interacting with others around 20 times per day. If we increase that, you'll see that obviously the disease is going to spread more quickly. Now, I don't know if 20 times a day is reasonable, but the combination of C and the next parameter, P, is actually consistent with what the data suggests. So P is the probability of getting sick when you interact. And it's really hard to separate those two things, how often people interact and the probability of getting of transmission during those interactions. So it's really the product of those two numbers that matters. And you'll see that, again, increasing the probability of transmission accelerates the epidemic and makes it much more severe. All right, the next parameter is D. That's the duration of the infection. So here it's set to be about 10 days on average before you either get better or you die. We can certainly make that longer. And notice that actually makes the predictions a little bit more dire because it gives people who are infected more chances to spread the disease before they recover. The next parameter is the mortality rate. That's how what percentage of people who get coronavirus will actually die from it. It's set to 3% right now, but you can reduce that or increase it, and you'll see that what that does is it changes the value of the green curve and the black curve. So as you increase the mortality rate, less people recover and more people die in the simulation. All right. Well, I hope that this persuades you to think twice before you ignore the advice for social distancing. And if you have any questions about the model, feel free to send me an email. The Hillsdale website has my contact information listed there, or you can follow me on Facebook. Thanks for listening.